We're going to switch over to accessibility. Accessibility research is a huge part of the HCIL, and that is reflected in the fact that we have 13 talks on it. So we're going to kick it off with Kyle. Sorry. So take it away.
Hi, everybody. My name is Kyle. Today I'm going to be going over some work with my great collaborators that we did, Trista Kyung-jung and Professor Hal Daume. This is some work we've worked on for about the past year and a half, and it's focusing on supporting blind users with visual question answering. So why do we care about this application? I think it's pretty obvious that an effective VQA system has the potential to revolutionize assistive technology for the visually impaired. However, most work with visual question answering really focuses on just improving models for like the standard challenge accuracy leaderboard and not so much on applications like visually impaired users. So our goal with this project was, can we define the differences between visual question answering for accessibility compared to models just focused on the leaderboard? And, will this help us guide research for designing future VQA models for the visually impaired? So this is just a quick example of kind of what the data looks like for the two different types. On the left-hand side, VQA V2 is the standard challenge accuracy that most people do. And on the right-hand side is the VisWiz, which is the visually impaired data set. And if we just take a look at the top row of the two questions regarding cats, how many paws do you see and what does this kitty cat look like? Please tell me the colors in his position. The question on the right is obviously a lot more in depth and requires a lot more complicated answer compared to just an answer of 2 for the one on the left. Therefore, this kind of gives an example of why visual question answering for the visually impaired can be more challenging. So we looked at 7 models over a 5-year period to compare kind of what their performance was on the standard challenge accuracy and if these improvements over time resulted in improvements on the visual question answering. And as you can see, there is a pretty significant gap between the two, with the blue being the standard challenge accuracy and then the orange and red being the visually impaired models. The visually impaired data set is also significantly smaller. So we also did on the standard challenge data set with the same size data set as the visually impaired to make sure it wasn't just a data set problem. For most models, up until the most recent model that we tested, it did seem that it might actually be a data size problem. However, for the most recent model, ALBEF, which is a transformer-based model, there is still a significant gap that persists. So we learned kind of 3 main areas where the models failed. First was overly generic ground truths. So models tended to predict more specific answers than the generic ground truth annotators. So this is an example of a data point from the VisWiz data set with the question of what is this? And how the evaluation metric works for VQA is there's 10 human annotators that give an answer, and then they just do a matching metric to what the machine output answer is with the human annotators. So as we see here, one of our older models, MFB, answered flowers and got a pretty high score, almost perfect. And our newer model, ALBEF, said iris, which is objectively actually more correct because that is iris, but it gets a much lower score because only one annotator said that this was the answer, and therefore it makes it seem like the newer models are performing worse when they're really not. Another one is guessing on unanswerable questions. So models tend to make predictions on questions that a majority are unanswerable. So unanswerable is a completely fine response for an annotator to put down if they can't answer the question. However, our neural models like ALBEF tend to make predictions on this and tend to actually be right a lot of the times. ALBEF said medicine, but obtained a score of 0 because none of the annotators said medicine. And it's hard to see, but this is Panadol, which is medicine. So again, the models seem like they're not doing well when they actually are doing well. And finally, annotator disagreement. This one is just annotators disagree a lot, unfortunately. And so like for this answer of, what's the temperature on a dial of a stove or on an oven, there's a lot of variation among the annotators. So it makes it really hard to have models perform well when it's only going to match a limited amount of annotators because the annotators themselves don't agree. So just in summary, improvements for visual question answering for what we call machine understanding or the standard challenge accuracy have translated to increased performance in visual question answering for accessibility, but there's still a significant gap that persists. And we saw that the main problem with this is that the evaluation metrics are just not an effective method for evaluating VQA for the visually impaired. And this leads to seemingly poor overall performance, even if it's actually not that bad. So our future plans are inspect whether machine-generated clarifying questions, so kind of interactive between the human and the model, are helpful in assisting blind users in verifying correct models, and then hopefully also improving model accuracy overall. And you can't see it here, but I had contact information for me or one of my coworkers, Trista. It seems like it got cut off on the bottom. And I forgot to link to the paper, but in the back, we did actually win a paper award. So it's listed in the back of the pamphlet. So I think we're the first one there. So if you're interested in reading the paper or looking up either our names to contact us, please feel free to reach out. Thank you.
Thank you, Kyle. Congrats on the best paper. So next we have Zayu, I believe.
All right. Hello, everyone. I'm Zoyu Yan from Smart Effects Lab, Computer Science, UMD. And today I'm presenting you Tangible Grid. I'm going to start with a short video clip.
Text bracket detected, location at 86, bracket row length 2, bracket column length 3.
So Tangible Grid is a tangible web layout design tool for a blind user. This work is in collaboration with Jiasheng Li, Abrima Jarju, Ashut Jedi, and Huaishu Peng. This work was published at WIS 2022 as a full paper. So designing a web page layout is comparatively easy for sighted people, but almost impossible for blind people, mainly because the current assistive technologies doesn't really provide enough visual assessments towards the geometry informations, like where things are, how big things are, and what shapes they're in. Right. So in this work, we are trying to design a system that would enable blind people to understand and design their own web page layout with direct manipulation and also real-time feedback. So we conducted semi-structured interviews for detailed challenges in designing these systems, and then we went through 3 rounds of co-design session with our blind collaborator at Brema. And we went from a concept from the left-hand side towards a concrete system on the right-hand side. So let's dive into this system really quickly. So we have two main sets of components in the system. One is a baseboard, which is a 12 by 16 grid system with sensing and mechanical features built into it. This is representing a web canvas. And then we have a set of different brackets. So they mainly looks like the one in the middle. They're resizable rectangle brackets that the blind people can just grab and resize and put it onto the baseboard. And there are different tactile markers that we can put on top of them so that the blind people can recognize what type of element this is representing, if it's a text or it's an image, or if it's a video, etc. So to use this is really simple, is that blind people are going to just grab these brackets and bring it near the baseboard with the right size they feel about this element, and then bring it near to the baseboard, and then the magnets on the bottom of the brackets will snap the bracket towards the baseboard and self-align them to the grid. And the baseboard have the sensing ability so that it can sense the type, the size, the location of this web element that they put onto the baseboard, and speaks out the information in real time. So this is a short clip of that.
Figure bracket detected, location at 9.5, bracket row length 4, bracket column length 3. Text bracket detected, location at 10 and 9, bracket row length 3, bracket column length 3.
So obviously they're allowed to put multiple of them onto the baseboard to represent different elements, and they're also allowed to resize and relocate each of the element, and then the updated information will also be vocalized. Another short clip of that.
Text bracket detected, location at 5.9, bracket row length 3, bracket column length 8.
So this is basically how the system works, and then to understand how usable or what's the learning curve like for the blind people, we conducted user studies with 2 tasks, and then we involved 10 blind participants to try to use this system to understand or design their web page layout. We report that all of them were able to use this tool to accomplish what we asked them to, and they have comparably positive feedback towards how confident they are to use this tool to design their web page layout, or like the learning curves and etc. There are more details in the paper that is with the same title. I believe it's in the ECM Digital Library. So if you want to learn more about the system or the study, you can refer to that. There are a lot of things that we can build upon this current version of Tangible Grid. So on the system side, we can basically upgrade the hardware to accommodate more complex or responsive web page layout. We can also embed our system with current existing like web page designing tools that are existing, like WordPress or Google site, that blind people can actually put their content, the Flash and Meads, into these web page elements to make sure that they have an entire web page design from end to end. So this as a starting point of a tangible interface to help blind people to do graphical layout design. We want to inspire more of these usage of like tangible interfaces to make more accessibility technologies. So that's all for my presentation. Thank you.
Thank you, Zay. Thank you, Zayu. Okay, Jiasheng, coming up. You're going to be doing double duty. Two talks for the price of one.
Hi everyone, my name is Jiasheng Li from Small Artifacts Lab at the University of Maryland. I'm excited to present our work, Touch Ally. This work is in collaboration with Zeyu Yan, Ashley Shan, Jonathan Lazar, and my advisor, Huaishu Pen. So from self-service printing station on campus to food ordering kiosks in the restaurant, touchscreen devices have been widely used in public spaces for its convenience, time-saving, and independent. Here are 4 photos of public kiosk we took recently, and you can see each of them is equipped with a nice large touchscreen. However, there is one issue. All of these touchscreen devices are changed. Okay. All of these touchscreen devices are changed for blind and low vision people to access and operate because they don't have any accessible features. So in fact, this is a known issue. Current laws in the US, such as American with Disability Act, require touchscreen devices in the public space to be accessible to the blind users. And several lawsuits in the US have also compelled large companies to make their public touchscreen devices accessible. Despite this effort, however, a large proportion of existing new kiosks with touchscreens, like the 4 I showed, are still not inaccessible to the blind people. So to better understand this problem and how blind people interact with public touchscreen, we conduct a semi-structured interview with 9 blind participants. Each interview lasts around 30 minutes, and we ask participants questions related to their experience with the kiosks, and here below are our findings. Not surprisingly, all participants reported that they didn't use touchscreen-based kiosks. They either choose not to use them at all or seek assistance from sighted people. Participants mentioned 2 main barriers. First, it's hard for them to identify a touchscreen kiosk is accessible or not. Second, many existing kiosks are claimed to be accessible, but in fact, they are very difficult for blind people to use. Also, blind people have concerns about their privacy. So what are the possible solutions? One way would be better to have new bills or regulations that require all companies to make touchscreen devices accessible, but that needs time and a lot of effort, and that will not solve today's problem. So maybe there is a way that to make existing inaccessible touchscreen devices accessible to blind and low vision people. So here we present Touch Ally, a working prototype that allows blind people to use existing inaccessible touchscreen devices independently and with little effort. And here is how touch, okay. That is have some problem with the videos here. I will probably. Here is how Touch Ally works. So first, blind people will put the touch ally on the screens, and then touch ally will take 3 photos to locate the bot itself on the screen. Then blind people will use their smartphone to access the screen content and then choose what they want on their personal smartphones with accessibility tools. For example, voice over, screen talk this. So we also did a user study to better understand how blind users interact with the touch ally. The task involves 4 steps. First, place the touch ally robot on the screen. Second, find the correct key options from the smartphones. The third is choose the sugar level, and then finally confirm the order and complete the transaction. So after the study, all the participants were able to complete the T-ordering task. The average time of completion was 87.2 seconds. We also clicked Likert scale questions to quantify the result. And participants agree that putting the touch ally robot on the touchscreen is easy. And they believe that the touch ally can make them easier to use screen and protect their privacy. So that's the end of my presentation. Our project has been published on the CHI 2023. If you have any more questions and further detail, can refer to our paper. And thank you all. So, okay, next, apart from accessibility project, our lab also have a robot sensing project. So here, I'm excited to present another work category, relocatable unclosed wearables with fast, reliable, and precise locomotion. This work is in collaboration with Adam Sara, Tara Rahman, Ge Gao, and my advisor, Huai Shupen. So primarily, this work is motivated by one main question: where do we wear the wearables? From a scientific point of view, different locations on our body represent different kinds of opportunities for sensing, interaction, and perception. For example, sensors placed on the joint can be used to detect the movement and body position. And also the span can be used to detect and reinforce the postures. And the chest can be used to detect breathing. And a microphone near the neck can be used to detect chewing. Apart from all this, there are questions that can be asked about long-term comfort, accuracy, social acceptability, and so on. So when we have multiple points that need to be sensed or track people's behavior, do we need each location have one sensors? For example, people have smart watches, but that cannot move, right? So what if we could make one sensor move around the body? Then just one sensor can do all the jobs for that. So here we have Catacos, a railway robot system on the clothing that allows the wearable move around the human body freely, like the video. And Calico can move the cloth along your body in a fast, reliable, and precise manner. And with a customer 3D printed track and the turntable, Calico can reach any desired location on your body. For example, from the lower body to the upper body. And here we have the Calico. Next, let's see what can we do with the Calico. And here we use the Calico as a workout tracker. It can count the number of squats when you're doing the workout. And also by using the onboard sensor, it ensures that the back is parallel to the ground. So it can move. And also it can move to the elbow to track the push-ups. Yeah. And also you can also attach additional sensors on the Calico. For example, here we see the stethoscope head being used to perform on-demand oxygenation. So here is so it can listen to your heartbeat here. And here, by providing the continuous feedback, Calico can help someone while they are learning a dance move. If calico detects a mistake, it will turn back to its original point to indicate people to do the movement again. And in the future, we are also exploring some applications. For example, we have a fluffy cases for the calico, and that can be a personal companion to interact with. Yeah. So finally, the Calico project has been published on the Ubicom in 2022. For more detail, you can refer to the papers. And thanks for listening. Thank you.
Well, we're going to move on. So up next, we have Sparsh presenting on FormAlly.
Hi everyone, I'm Sparsh, and today we'll be talking about FormAlly, which is a tool used for making PDF forms accessible. So first, let's learn a little bit about PDF form accessibility. So you must have seen PDF forms being used across different industries in healthcare, education, and governance. In fact, if you see here form on the left, it's a ballot PDF form, and it might be used for voting. And the form that you see on the right side is a form from the Department of Veterans Affairs and might be used for gaining benefits by a veteran. Now, even though these PDF forms exist all around us, most of the PDF forms that we find on the internet are not accessible. Why? Because PDF forms are not born accessible. Essentially, you need to perform some actions and provide some metadata to these forms to make them accessible. So let's look at the process of making them accessible. So first you need to see what are the different fields that exist in a form. Once you have identified a field, you need to create a bounding box around it, and you need to specify what kind of data will go inside this PDF field. In this field, it could be a text box, a date field, a signature box, or whatever else it could be. Second, you need to identify all the groupable fields like radio boxes and check boxes, and then you need to define that this is a group. And finally, you need to mention something called as a tooltip. Tooltip is the text that gets read by a screen reader when focus enters a field. So imagine someone pressing tab and entering a first name field, and first name as the text will be read out to the user. Now, these three steps might seem super easy, but someone who is making a PDF form accessible has to do them repeatedly again and again for all the fields in a form. So if you look at the form towards the right, it has 70 or 80 fields. And this is just one page of the field. This form might have multiple pages. And you can also see that it is really high in density. And in these cases, it becomes super hard to make the form accessible. And this is made even harder because of this, the tool. Adobe Acrobat is the industry standard tool used for making PDF forms accessible. However, when we went to new users and experienced users, we found out a lot of issues that they faced while using this tool. For new users, the tool did not direct them around how to start making PDF forms accessible. And for experienced user, it gave them a lot of usability issues, and it was really cognitively demanding. So we created FormAlly, which is more like a wizard-like linearized tool, which makes the whole process of making PDF forms accessible super easy. So as you can see on the top, it just takes you through a linearized process, first making fields accessible, then groups, and then tooltips. And last year in HCIL Symposium, we provided an in-depth demo of this tool. So we thought that this year we share with you the study that we performed on this tool to find out its efficiency and effectiveness against Adobe Acrobat. We performed a within subject study with 20 participants, where each participant was asked to use both Adobe Acrobat and FormAlly. And we ensured that we provided 2 forms to both the participants, where both forms had similar complexity. And we changed the order of the tools and forms for all the users so that we don't run into any learning effect with the users. And we eventually find out that formally outperformed Acrobat in both time and task performance. It took on an average of 31 minutes to finish the task in Acrobat. However, in formally, the time required was just 12 minutes. Further, the task accuracy in formally was 25% higher, and the amount of errors that were introduced while performing the task was 5 times lesser. Finally, we also wanted to learn about the usability of the system. So we also provided our users with a SES questionnaire, and we found out that the SES score for Formally was 83, and for Acrobat just 45. Anything above 80 is considered usable, which made Formally much more usable as compared to Acrobat. And finally, I'd like to thank our sponsors at Adobe Research and Nidaler. And yeah, we are currently in the process of writing this paper, and I hope Adobe sees this and incorporates in Adobe Acrobat soon. Thank you.
Thank you, Sparsh. Always nice to see progress from year to year being made. It's always great. So, Ree, you want to come up?
Hi, everyone. My name is Ria Kamikubo. I'm excited to share with you our work on contributing to accessibility datasets, where I'll present reflections by blind people on sharing their study data. This is joint work with my fellow PhD student, Kyunjin Lee, who just graduated this week and is now at Google, and our PhD advisor, Hanisa Katsuri. Yeah, so we're members of the Trace Center and also, of course, HCIL, and this work is supported by Nidaler. So let's begin. So this talk is all about accessibility data sets, and to define what we mean by that, they are data sourced from disabled people that have the potential for training and testing machine learning models. And in this work, we focus on images taken by blind people. So why do such data sets matter? So first, there we go. Okay, they are critical. They're central to innovation. Let's see. Photos taken by blind individuals can be used to train our mobile phone to recognize everyday objects, increasing the access to our visual world. Such data sets could also help in mitigating AI bias so that people who may face difficulty in camera framing or avoiding object occlusion, those images can be detected, can be recognized. And so they could help broadly deploy AI systems to be effective for diverse user populations. However, if you're interested in finding these accessibility data sets, you'll quickly realize they're scarce. And so how can we change that? And generally speaking, privacy concerns raise tensions in data sharing, data collection and sharing practices. And for creating and sharing accessibility data sets, one has to carefully consider the added challenges. So first, collecting data from small population increases the risk of re-identification. And this can amplify concerns for non-consenting disclosure relating to a sensitive disability status, which can lead to further discrimination risk. And lastly, sharing accessibility data sets also poses risk of data misuse and data abuse and misuse. People could reuse these data with the wrong intent, such as building an algorithm to detect or misdetect a disability without one's consent. So if you want to know how to share data sets from your study and how to involve your participants in that process, we hope this work can shed some light. We interviewed 13 blind people and had direct conversations on how their study data could be shared. The focus was mostly on photos and labels of everyday objects. However, we also included questions on demographics, voice recordings, and broader set of data that typically collected in user studies. And perhaps you could borrow our questionnaire and adapt it to your study and your community. So an innovative aspect of our work is that we contextualize the interview in this actual deployment study. Participants were first invited to evaluate an object recognizer deployed on smart glasses in their homes. And they generated photos and labels of everyday objects to personalize this AI-infused application. And as a follow-up, participants reacted to various factors that could influence their decision to share their study data. And last and most importantly, they were called to decide on whether they want the researchers, which is us, to share their study data so that we were able to act on their decisions. And we gained so many insights from this interview, and we invite you all to read our paper published at CHI 2023. Sorry about the formatting here. And in brief, we found interesting ways blind people assess benefit-risk trade-offs when it comes to sharing their study data. And they also express concerns over ambiguous data use. So for example, many participants were not sure why would someone need to know the gender or race information of those who contributing their data. And lastly, loss of control once they share their study data was also critical. They wanted to restrict the use cases as much as possible, but were aware that there's no mechanism for it, so they gave up. On that positive note, we invite you all to start involving your participants in shaping your data practices. What we attempted in this study was to have our participants consent on their data at the end, once they have a chance to go over their data and reflect on them. And we certainly can do more. Thank you for listening.
Thank you, Ree. We're going to move on to Jung Ho.
My name is Jung Ho Lee, and I'm a second-year PhD student at the Information Studies program. And I'd like to present our ongoing research on multimodal activity tracking to support stroke rehabilitation on behalf of my collaborators, Dr. Ivan Lee from University of Massachusetts, and my advisor, Dr. Eun-kyung Choi, here at University of Maryland. So stroke is a leading cause of disability in the US, where more than 700,000 people suffer it every year. It's usually caused when blood supply is blocked to a part of the brain, which causes oxygen deprivation and eventual damage to the brain. Stroke can cause a variety of long-term health effects, including paralysis and motor impairment on either side of the body, depending on which part of the brain loses oxygen, speech or language disabilities such as aphasia, and thinking or trouble thinking and memory problems. Stroke survivors engage with a variety of rehabilitation programs to relearn daily activities. Some of these programs include physical and occupational therapy, speech therapy, and then the important part in the whole therapy process is the initial goal setting, where the therapist and the client identify goals that they would like to achieve together. Patient-centered goal-setting technologies exist, but there are problems in engaging stroke survivors when setting personally meaningful goals for more effective therapy. Research in personal informatics show that tracking various aspects of one's life can help lead to self-discovery. Drawing from this prior knowledge, we became interested in investigating whether keeping a journal of daily activities can help stroke survivors think about what activities are meaningful to them and help them engage better in the whole goal-setting process. Furthermore, mobile apps are often used in self-tracking technology due to their convenience, but not much is known about their accessibility for stroke survivors. Thus, we guide our research with these two research questions. How can activity tracking support goal setting for stroke rehabilitation? And how can using a combination of voice and touch help improve accessibility for these activity tracking apps? To test our ideas, we developed GoalTrack, an Android app that lets users track their daily activities. It prompts the user to log an activity that they would like to improve on and any challenges that they encounter while doing the activity. And in addition to unstructured data, such as those sentences, the user can label structured data, such as the label of an activity that they would like to add it to and the overall time and duration of the activity. The highlight of our design is the ability to log activities using a combination of both speech and touch. So stroke survivors can use their voice to transcribe sentences and input other types of data. Using our prototype, we designed an in-person usability study and started recruiting stroke survivors who had stroke more than 6 months ago. We would call our participants before the actual day of our study to ask how their day has been going. And during the actual session, we provide a short tutorial of our app, then ask the participants to log activities from the day before. And we asked them to participate in a semi-structured interview afterwards. We conducted the study with 9 stroke survivors so far by contacting local stroke support groups and sending flyers over emailing lists. We are still digesting our data, but I wanted to highlight a couple of initial insights today. First one I'd like to highlight is how multimodal input can be really helpful for stroke survivors logging activities, even for those with no or limited prior experience using it. Participants also reported that using their voice was easier to log activities than using the virtual keyboard. Most of our participants had motor impairments on either side of the body and had trouble using both of their hands. And using the voice interface was really helpful for them to augment the touch input. Another interesting thing was that voice interfaces can actually help stroke survivors who struggle with language by helping out with drafting out thoughts or helping out with spelling. Lastly, participants reported how the prompts and the actual act of logging activities helped them think about which activities were important to them. Thank you so much for coming to my talk. I think you'll find the next talk to be very similar. But the key takeaway is from this talk is to see how multimodal input can help actually inputting data to this technology. And I welcome you to visit our poster. Thank you.
Nice way to transition. Aishwarya, you want to come up?
Hello, everybody. Like Jungho said, very related project. I'm Aishwarya Shedigar, and I'm a recently graduated grad student in the iSchool. And I'll be presenting our work exploring how audio narratives can complement visualizations of stroke survivors' personal health data. And I'm presenting my work on behalf of advisors Dr. Eun-Kyung Choi and Ivan Lee from UMass Amherst. So a little bit about stroke and specifically about how complex stroke recovery in the chronic stage can be. There's things like hemiparesis, which when a stroke happens, sometimes stroke survivors can experience loss of function and motor weaknesses on one side of their body. This is called hemiparesis. They can also be affected by other types of recovery challenges like aphasia, visual spatial disorders, and others. And these are not mutually exclusive, so one stroke survivor may experience all of these or a combination of these and makes for a very complex recovery. One of the ongoing tools in development for helping stroke survivors who experience hemiparesis is something called a wearable ring sensor, which can monitor how much they're using the side of their body that was affected by the stroke, and then the side that was unaffected, and put those two together to see how they're progressing in their recovery. And you can see one visualization at the bottom showing this sort of ratio between the affected side of their body and the unaffected side. And this awareness can help stroke survivors build a program and continue to progress. However, because stroke survivors can experience so many different challenges in their recovery, delivering feedback effectively can be difficult, especially if people have different perceptual losses. So in this project, we investigate how using multimodal outputs can help stroke survivors better understand the feedback coming from these wearable technologies. And in this project, we looked at two, so visual based off of previous work in charts, and then audio based on these speech-based narratives that we developed with 4 clinical perspectives, so 4 occupational and physical therapists. Coming together, that brings us to our research question: how can speech-based audio narratives complement visualizations of stroke survivors' personal health data? And just to give an idea of the method that we used, I really wanted to use co-design with this population. And we did it remotely. So on the left side, you can see the researcher perspective. I would be moving my mouse and conducting the co-design activity on my screen, and the participants would be driving the conversation on their end. So we had 10 stroke survivors who experienced hemiparesis and some other perceptual disorders too. They might have been accompanied by their caregiver if they wished to, but they would be driving the conversation and telling me sort of what changes to make, what design ideas they want to incorporate, and we worked on it together. And then these are some of the artifacts that came out of that co-design process. And if you come visit our poster, you can see these in a bit more detail. But I'll highlight some key findings. And firstly, I'll highlight key findings related to how the two modalities mixed together and how multimodality worked. So across the board, people wanted really rich data descriptions when the audio was used with the visual. They didn't just want alt text. They wanted something more that could really help them guide their recovery. Things like positively framed encouragement were well liked across the board, and things like reflection prompts, guidance, clinical suggestions were effective, but they need a little bit more tweaking and work to be actually effective. And then some key findings related to how unique the stroke context is. We found that some mathematical terms, like more and less, if you're describing quantities in relation to each other, can actually be very difficult to understand for people who have an acquired condition called acalculia, where they have difficulty understanding mathematical relationships. Some people said that the audio modality can even help them with their aphasia recovery exercises. And then I'll just speak briefly about the chronic recovery process. We had mixed reactions from folks who were earlier in their recovery process versus later. So people early in their process responded well to the audio narratives because they had not heard this messaging before, but they did not experience too many, recovery wins, so they might not buy into the success of the feedback. People who are later in their recovery, on the other hand, were more desensitized to these same audio messages. So it was a little bit difficult for them to buy into the audio as well. And with that, I will go to our last slide, which has some takeaways. And then if you have any questions or would like to see more findings, please come find our poster. Thank you.
Galina and Scott, you want to come up?
Good afternoon, everyone. I'm Galina. I'm a faculty at the iSchool.
And I'm Scott. I'm a graduate student in the Information Management program.
We are so excited to talk to you today about a class that we taught on voice technology and how we feel University of Maryland students are revolutionizing design and design for voice first. And we're very excited about this course because it is very innovative. First of its kind that's been offered at the University of Maryland. And we had a large amount of students for both semesters that we taught this course. And it was a very diverse group of students, not only information science, but computer science. We had real estate development majors, so all walks of life and experience. And we felt like it's a great way to expose these students to voice technology, to accessibility, and how to design and really experiment and utilize all of these HCI principles that we know and love, but really expose these students to them. This class was very much influenced by my research in voice technology, specifically Alexa, and how Alexa can support the lives of older adults who have dementia and their care partners. If you're interested in papers, happy to share, but this class was really focused on making sure that we expose young students to this type of work and application. And Scott was really instrumental in teaching students on how to utilize VoiceFlow, the platform that we used to teach them how to build skills for Alexa. They did a phenomenal job, which is why we're excited to present some of their projects to you today. We felt like voice was very much an underutilized space, and we hope that this class will reach not only undergraduate students, but graduate students, build collaborations and relationships, and really kind of take a different perspective on HCI work and development. And so I'll hand it off to Scott, and he'll showcase some of our favorite projects to you.
Thank you. Hi, everyone. Okay, so some background. So Alexa skills, they're like smartphone apps for your conversational assistant. And so VoiceFlow gave our students the ability to become third-party developers in making Alexa skills. They designed on VoiceFlow their conversational assistants and were able to export their work to the Amazon Alexa virtual developer kit. And so VoiceFlow, it's a visual canvas that makes everything accessible to designers and non-designers alike. Textual coding is not required to make a conversational assistant with this platform. And it empowered all of our students to get involved in the design process because not all the students have a background in IT. Graphical tools in VoiceFlow's workspace are used to make a flowchart. And VoiceFlow is programmed by dragging and editing content of cell blocks to create a flowchart of user interactions. You can use menus for each block to customize the behavior. Also, students were able to leverage the GPT AI plugin in VoiceFlow to help with error checking and keep the conversations with users running. This was especially helpful when the user responds in a way it was not explicitly programmed for. Yep. And so over the course of the spring semester, our students worked on finding a way to address a problem in the accessibility community with Alexa skill and conducted interviews with end users to identify a need within a specific group of the accessibility community. Okay, so this is the Care App Assistant, and you can see here just a screenshot of one of the prototypes. And it gives caregivers and older adults an easily accessible way to get reminders and be told of upcoming daily tasks and add new ones, as well as contact relatives. This one's called MedAsk, and this project team created a VUI that assists older adults with memory loss issues, such as dementia and Alzheimer's, with daily medication tracking. It provides users with descriptions of prescribed medicines and the purposes. It also gives family members alerts if they've taken the medicine. And then this one is, again, for older adults with dementia, and it just gives them voice reminders about scheduled daily tasks and add new ones. Here you can see a screenshot, and this is just the graphic of the Canvas workspace in VoiceFlow. And then the very last one is a VOI skill for the hearing impaired audiences. Helps users with volume control, connecting Bluetooth seamlessly, touchscreen to allow users to interact without speaking, and better language comprehension. Okay. And thank you all. So we have QR codes here where you can view the students' projects and see them in VoiceFlow.
Thanks, everyone.
Thank you both. Julio, you want to come up?
It is 5:30 p.m. As Andy is heading out from work, and to the eyes of many people, Andy is living a very happy life because they have a lot of friends, they practice a lot of sports, and they have a great job. Unfortunately, Andy is going through an abusive relationship, and people do not know that. In fact, Andy does not realize that they are going through an abusive relationship because of their strong emotional attachment to their partner. Good afternoon, everyone. Today, my colleague Monging and I, Julio, will be sharing our project whose main goal is to design an mHealth app to support survivors of domestic violence self-reflect on their relationship and well-being based on their physiological data and provided data such as emotion state and daily routine. Domestic violence, or DV, is defined as patterns of behavior in the context of a relationship in which one individual seeks to obtain and maintain power and control over the other individual. DV groups various types of abuses, including but not limited to physical, psychological, and economic abuse. Prior work has proposed different technologies to help survivors, including mobile applications like MyPlan and Tidy Home. MyPlan, for example, allows survivors to do safety planning as they are trying to move out of an abusive relationship. And Tidy Home has features like an emergency button and a third ear recorder that allows survivors to reach out for help in case of an emergency. In this project, we're taking a more preventive approach to tackle domestic violence.
So in our project, based on the literature review and received feedback from researchers who did a related work similarly, we designed Sana, an mHealth app that integrates physiological data to help users self-reflect on their relationship at an early stage. So you can see This is our prototype right now, and we take into considerations in our design that our target users may still living with abusers, and they may be hypervigilant and traumatized. So Sana looks like a fitness app at first sight, but here we designed a hidden mode that users can use an invisible gesture password to enter into the main interface of our app, where they can record how and why they have been feeling, as well as monitor their physiological data and respond to prompts that related to the significant times that detected in their physiological data history. So all this can be helpful for our users to self-reflect on their relationship. We are currently recruiting caseworkers and survivors as participants to improve Sana and ensure the user safety.
In summary, Sana will help people like Andy to realize that they are going through an abusive relationship. It is important to highlight that our goal is not to replace human caseworkers, but to encourage survivors to reach out for help sooner. We would like to thank our collaborators Jing Wang and Sanchita Shuk, and our advisor, Professor Yong Kyung. If you're interested in learning more about Sana, come talk to us during our poster session. Thank you.
Okay, Jarrett, you want to come down? You're next.
Hi, I'm Jarrett Lee. Happy to present our work with my co-authors Bangchun Lee and Eunkyung Chae, which we recently presented at CHI 23. Research has shown that health often responds well to a balanced and consistent schedule. So today there are several systems that notify users towards regularity in many health factors. But let's take an example of a medication alert. And it's easy to imagine someone being so busy that they missed a notification altogether. So how do we ensure that the user receives a message? One way is disruptive, where you have alarms, like a very loud alarm. But we probably shouldn't have a disruptive alarm that forces the user to act, because generally it's not that important. Take your dose at that very second that your notification is scheduled. But if we repeat the alarm maybe at another time, we could be interrupting our user multiple times now, and this could cause messaging fatigue, especially if the user might have a legitimate reason for not acting on this alarm notification. We could think about an ambient system, such as an alarm clock that uses light, something that's non-alarming, I guess. This could help with our first two problems because it uses a non-distracting notification style. It doesn't break their attention. That's good, but now there's a point in time where you actually have to take your medication. So using only ambient notifications might not be able to alert the user appropriately. So to help with these situations, we introduced the term of abruptive technology, or ambient to disruptive technology. So these systems initially use the ambient notification messaging, but are capable of increasing their notification levels to disruptive if the message becomes more critical. And to validate this idea, we wanted a concrete example to explain this abstract concept with our users. So we took a research through design approach, and we created a series of shape-changing interface artifacts to help with this idea. And we modeled our artifacts after plants because we thought that because plants are so ubiquitous in homes and offices, this would help with the ambience levels. Here's the first artifact, shake artifact. So this is meant to represent winds blowing through the leaves at various levels. We have subtle shake and heavy shake motion. And we picked these to explore differences in distance and speed and how those affect noticeability. We have a second artifact, droop artifact. This can lift or drop its stems to various levels, and we scripted 4 different motions in this artifact. Here's heartbeat and hiccup. And we could also use those for speed and distance factors, but we also meant to see if we could explore motions that could elicit emotional responses from the participants. And with this same artifact, here we go. And this same artifact, we have these last 2 motions. We want to explore saliency by comparison of natural to unnatural looking movements. So here's lift and panting. So our paper discusses various situations that our participant deemed worthy of being interrupted for. Some aspects such as medical severity and time criticality were important, but users were also accepting disruption if they felt the systems could calculate their notifications to fit their schedule, or if they would optimize results based on historical behavior. But we also learned additional lessons in how our various design choices made our artifacts, changed how our artifacts were picked up by our participants and how they reacted to it. So for instance, when this droop artifact moved down to this downward position, many interpreted this as the plant dying. And this was accompanied by very morose reactions, so strong that many said that they would stop using the system altogether. Reactions were explained as being caused by sad reminders of plant caretaking, former failures in plant caretaking in the past, or mirroring empathy given to their own houseplants that had gotten ill. Panting motion here gave even stronger reactions. Some people thought it had discomfort stemming from the uncanny valley. We think is the first instance of uncanny reactions to a non-zoomorphic item. Because we portrayed this item as a plant, or our system as a plant, it came with expectations of how it could move. And this motion here clashed strongly against that expectation. We also gained design insights in physical systems, such as these artifacts, shape-changing artifacts, such as how the plant-like aesthetics alone gave value for the decorative use. So even if the interest in their notification system, notification portion faded, these systems could be still left to remain in place. And doing so, it could be given time to for interest to build once more into its original function and allowing for extended use. And we call this disinterest buffering. Our discussion section includes the next steps for inductive research, more design suggestions and physical interfaces, and how these artifacts might be used for detailed investigations into negative and uncanny reactions. And we invite you to explore our paper for more details. Thank you.
Thank you, Jarrett. The panting plant always freaks me out. I don't know if it's like horror movie, whatnot, but oof. Okay, I think Priyanka's next.
All right, hello everyone. My name is Priyanka. This is my collaborator Nee, and we worked this past semester on a value engineering project under Professor Paredes, who recently joined the HCI lab. So this is a project that basically talks about redefining health interventions. So let's say that you, just like billions of people across the world, have been spending far too much time on social media. You find yourself endlessly scrolling Facebook posts, Instagram reels, tweets, or even TikToks. Now, you see an app that tells you, hey, how about you only look at social media while you're exercising? So you, in your infinite wisdom, then realize that your only form of exercise is swimming. So this isn't going to really work well for you. Or even better, you don't really take time out of your day for exercise because your 20-minute bike ride to College Park is enough. So in this case, we see that some of these interventions fail. This is because that mobile apps and wearables, while having made recent strides in prompting targeted behaviors, don't really take into account user values and priorities. So we don't really understand what kinds of behaviors are going to work in forms of interventions. And in that way, we now aim to formulate a domain-centered value engineering that aids tailored interventions. So how can we better provide interventions to users that we know are going to work based on our understanding of user behaviors and values?
So values are a very fundamental component of all of our lives. They encompass all of our beliefs and can guide our decision-making and our behaviors. These beliefs and principles are shaped by different factors, such as like your cultural upbringing, your personal experiences, your religion. These factors are deeply ingrained within our individual priorities and can be reflected in our goals, aspirations, and motivations. So on the left, you'll see Schwartz's theory of basic human values, which is basically a cross-cultural framework that identifies basic values and their motivations. The core idea is that particular values are can inherently conflict or align with other values, and these dynamic relationships are typically illustrated using a circle in which opposite sides indicate conflicting values. These values are seen as not only important for individual decision-making, but also have an impact on group dynamics, social norms, and institutions. The issue with this model is that it's linked only to human behavior, and you can't really apply it to real-world situations, which leads us to our second contribution of this work, the application of value domains. This is primarily utilized in a psychological setting, and the value domain framework differs from a traditional understanding of human values and behavior by providing interpretable categorizations of human actions into domains. While the values in the original theory are rooted in abstraction and often difficult to quantify in day-to-day life, these domains are intended to be exhaustive and directly associated with the different ways in which people can spend their time. The intention behind this framework is to facilitate a better understanding of human values, specifically in a computational research and mobile application setting. So what exactly is value engineering? Well, values dictate our behaviors. Technology can assess values to engineer long-lasting behavior change.
Yeah, so really quickly, the idea here is that everything we do on a day-to-day basis is rooted in our core values, right? What is it that we value? How is it that we want to spend our time? And so if we can adequately use technology to assess these values, then when we can actually truly engineer long-lasting change, as opposed to these really short bursts of energy that we get to fix our habits that we then eventually lapse from. So the question here is really, can we effectively promote behavior that aligns your values with your priorities? Can I provide you with interventions that you are actually intrinsically motivated to follow, so that you don't usually pick a habit up for a week and then drop it because it's not something that really fits into your lifestyle? So the first step in our methodology here is to assess our values. So we provide our users with an assessment that basically understands, according to our new framework that we've devised, how people spend their day, what their values are. So there are 9 main domains in this framework that are basically meant to be exhaustive and indicating that how someone is spending their day. So these include familial, social relationships, as well as leisure time, recreation, and personal growth. So once we have an assessment of someone's values, we can then use it to record their screen time and provide personalized interventions based on their daily reflections of their values and intended priorities. Thank you so much.
Okay, last but certainly not least in our accessibility track, we have Yoon Kyung. Want to come down?
Hi, everyone. My name is Yoon, and I'm currently working with Professor Pablo. And this is our project called Designing a Just-in-Time Intervention Method for Onychophasia. So, as you can see in this photo, onychophasia is a body-focused repetitive behavior where people compulsively bite or chew their nails to avoid or alleviate their negative emotions. And it's also considered as obsessive compulsive disorder. And around 20 to 30% of people engage in nail biting when they're feeling nervous, anxious, or frustrated, or even bored. But if you take it to the extreme, then this is how the nail will look like. It's a little gross. So there are infections around the nails and blood in cuticles. And so these are what the nail biting causes for the physical problem, but also mental problem is that it's not really actually solve the negative emotions what people feels. So our research question is that can we use technology to provide some long-term help in stopping nail biting? And can we use some AI in the cyber physical system to manage and treat onychophasia effectively? So we first start with the behavior detection. So these are early prototype of our computer vision approach. So we try to distinguish the normal behavior, nail biting behavior, and also other hand-related gestures such as resting chin on hand. Sorry that I look very tired. And we provide two types of interventions here. First is active intervention, and second is proactive intervention. So for the active intervention, we utilize electrical muscle stimulation to prevent the nail biting. And this is the early prototype of VMS device that this is supported by Jun Nishida. And by using this, we can make people clench their fists or stretch their fingers, or we can even manipulate their arm trajectory to keep the distance between mouth and hand. And for the proactive intervention, we provide some sensory stimulation as a guide or some distraction to help them to regulate their emotions. So before we actually start implementing the device, we wanted to obtain some ideas from real nail biters. So we conducted the survey, and this is one of the questions from the survey. We asked, if you were provided with some kind of stimulation, how do you want to use it for instead of nail biting? And all nail biters participated in our research, in our survey, answered that they prefer distraction and guide over punishment and alarm. But among them, severe nail biters preferred the distraction and punishment over guide and alarm, which is very interesting that severe nail biters prefers punishment. It means that they have reached at the point that no other method really works for them. And we also asked, so what kind of stimulation do you want to feel on each body parts? So severe nail biters answered that they want to feel some pain around the jaw area, or some taste in mouth, or some vibration around the finger and hand area. So based on this survey result, we're now in the stage of creating some prototypes. So we'll do some co-design process by doing some interview and also obtain some knowledge by meeting the actual severe nail biters. And we will finalize our intervention method and do some evaluation later. So we're currently recruiting some participants for our co-design process. So if you're interested, please contact me here. And thank you.